So we're building up to solving a second order differential equation in terms of power series, but we need to go through some theory and definitions first. So suppose we have a differential equation. Okay, notice this is second order and it's written this way. If we were to divide everything by that a2, then we could rewrite this as y double prime plus a1 of x divided by a2 of x times y prime plus a naught x over a 2 of x times y is equal to 0. So that division will be valid as long as that a 2 of x is not 0. And then if we do write it this way, this guy is just another polynomial, which we could, or function rather, that we could call p of x. This guy is another function, we could write it as q of x. So then we can condense that a little bit further as y double prime plus p of x y prime plus q of x y is equal to 0. So now let's talk about ordinary points and singular points. So a point is ordinary if, when we look at that differential equation, that p and q is really just not going to have any issues plugging that number in. Remember, we can't divide by 0. So another way of saying that is it's ordinary if we're analytic at that point. And analytic basically just means that we can find the derivative at that point. Going back to the last section, when we were talking about analytic at a point, it said that we could write it as a power series. In x minus a So if we have something that's analytic, then it's going to be differentiable. So there's a connection there also. Now, we have a singular point if it's not ordinary. And what's going to happen with a singular point is we're going to have an issue here because there's going to be a place where that guy's going to be equal to 0. And we know we can't divide by 0. So we'll see an example of that in just a few minutes. So let's look at a few examples. We have a homogeneous linear second order differential equation with constant coefficients. Okay, both of these guys are second order linear with constant coefficients. So there are no singular points here. We don't have any issues where, think about domain restrictions. We don't have any kind of domain restrictions for that p of x or that q of x. Notice these are written in what we've been calling all semester proper form, where we have a 1 as that leading coefficient in front of that y double prime. So we always want to think about it in that form. So, same example. That means that every x value here will be considered an ordinary point for something that looks like this. And it actually doesn't matter what those coefficients are. If they are constant coefficients, then you're not going to have any kind of issues here. Okay, obviously, this guy's going to have to be a 1 for it to be a second order differential equation, or some other number other than 0. Now let's look at another one. Now we've got some coefficients that are functions. Okay, this guy's in proper form. We have a 1 as the coefficient in front of the y double prime. We're not going to have any kind of restrictions here. E to the x is going to be fine. It's defined everywhere. Sine of x is defined everywhere. So all of our x values here are going to be considered ordinary points because we don't really have any kind of domain restrictions. So if we want to look at something like x equals 0 specifically, it's going to be an ordinary point for this, just because we could express e to the x and sine of x in terms of a power series that's centered at 0. So it's analytic at that point. Now let's look at this one. So we have y double prime plus xy prime plus the ln of x times y is equal to 0. So this one's a little bit more interesting than the last few. We still have functions as coefficients here. X is going to be analytic at every real number. Ln of x does have domain restrictions. It's going to be analytic at every positive real number. So remember, the domain for this has to be x values greater than 0. So notice that the ln of x doesn't include 0 in its domain, which means it's not continuous at 0. So we can't write that as a power series that's centered at 0 because 0 is not in the domain for that function. So then we can say that 0 is going to be a singular point of the differential equation, all because 0 is not in the domain for that ln of x. Now let's look at this guy. This guy's not in proper form. We have an x as that leading coefficient here. So if we were to divide everything by x, then we would get y prime plus 1 over x, y double prime plus 1 over x times y prime plus y is equal to 0. But because we divided by x, we've now introduced some domain issues. Let's look at our p of x function. Our p of x is 1 over x. And we know this guy's going to have an issue at 0 because it's not defined at 0. So then we would say 0 is a singular point for this differential equation. So let's look at some conclusions. A polynomial function is going to be analytic at any value of x. A rational function is analytic except at points where that denominator is undefined. So that's where you're going to have those domain restrictions. Okay, and I want you to think about analytic kind of like, can I take the derivative of it at that point? Polynomials don't have any issues because we can take the derivative anywhere. Domain's all real numbers. Rational functions, we can take the derivative anywhere except where that derivative is undefined. Same thing's going to be true when we talk about analytic functions. So if we are taking this differential equation and we're dividing everything by a2 of x to get this, then p of x is going to be a1 of x over a2 of x. And then q of x is equal to a naught x over a2 of x. So if we're looking at our p of x being that ratio, a1 of x over a2 of x, and q of x as being a naught x over a2 of x, which is just coming from taking this differential equation and putting it in proper form, where we have a 1 as that leading coefficient, then it's really going to be analytic everywhere except where that denominator is going to be equal to 0. So then a number that's an ordinary point is really anywhere that's defined in the domain for that p of x and that q of x. So as long as this guy's not 0, we're good. But anywhere that is 0, we would call that a singular point. So let's look at a few examples. Let's say we have this guy and we want to find values where we're going to have singular points and ordinary points. So just like when we talk about domain restrictions for rational functions or something like that, it's almost easier to identify where you would have issues and then everything else is good. So we would start this guy by dividing by that x squared minus 1. So we're going to have y double prime plus 2x over x squared minus 1 times y prime plus 6 over x squared minus 1 times y is equal to 0. Because we've divided by that a2 of x, now we've introduced some domain restrictions. So we are going to be singular anywhere that denominator is going to be 0, and that's going to happen at plus and minus 1. Everything else is going to be fine, so everything else we would call ordinary. So we're going to say we're ordinary everywhere else. Let's look at that next one. We would divide everything by x squared. So we're going to have y double prime plus y over x squared is equal to 0. So we're going to be singular at 0. That's where that denominator would be 0. And it's ordinary everywhere else. Now let's talk about this guy. Same kind of concept. Divide everything by x squared plus 1. So if we're thinking about the complex plane, there are some places where we're going to be singular. We're going to be singular where x squared plus 1 is equal to 0, or x is equal to plus and minus I. It's going to be ordinary everywhere else. So now let's look at a theorem that's going to guarantee us existence of a power series solution. So if x is equal to x naught is an ordinary point of a differential equation, we can always find two linearly independent solutions in the form of a power series that's going to look like this. Okay, keep in mind we're talking about a second order differential equation here. Okay, so that's why they're saying two linearly independent solutions. If this were a third order, then we would be able to find 3. If it's fourth order, we could find 4, and so on. So the power series solution is going to converge at least on some interval defined by this kind of radius of convergence here, where x naught is going to be the closest singular point. So a solution that's of this form is said to be a solution about the ordinary point x naught. And that distance r is going to be the minimum value or the lower bound for the radius of convergence. So we're trying to minimize that distance there. We think about that in terms of some kind of number line. So let's look at a few examples. Now I actually want to start with the second example first. So we want to find the minimum radius of convergence of a power series solution of the second order differential equation about the ordinary point x equals 0, and then about the ordinary point x equals 1. So we've got two parts to this problem here. So let's find those singular points. If we were to divide everything by that x squared minus 25 to put this in proper form, then our denominator would be x squared minus 25. It's the same concept as setting a2 of x equal to 0, since we would have to divide by that a2 of x. So that's going to give us two singular points, one at positive 5 and one at negative 5. So think about this in terms of a number line. Here's our singular points, negative 5 and positive 5. We want the minimum distance, or the minimum radius of convergence. And let's start with x equals 0. So I'll call that part A. So what's the minimum distance from 0 to 5? Well, the minimum distance is going to be the straight line between here. So that would be 5 units. So that would be our minimum radius of convergence. Well, what if we were to change this to be ordinary about 1? So 1 would be here. Now our distance has changed. The distance from 1 to 5 is 4 units. The distance from negative 5 to 1 is 6 units. We want that minimum. And so that minimum would be 4. We're just looking for that minimum distance there. Smallest distance between our ordinary point and then our singular point. Now let's go back up to this one. This one's going to be a little bit more interesting. So we need to find singular points first. So we're going to set that equal to 0. That's our a2 of x. If we were to put this in proper form, we would have to divide by that guy. So that would be in the denominator. That's why we're setting it equal to 0. To solve this, we're going to have to use the quadratic formula. So it's going to be negative b plus or minus square root b squared minus 4ac over 2a. 4 minus 20 is a minus 16. So this is 2 plus or minus 4i over 2. So we get 1 plus or minus 2i. So there's our singular points. Okay, and they are complex in this case. So now we want to find that minimum distance. We know from theorem 6.2.1, we're guaranteed 2 power solutions centered at 0. So then they've got to converge. Where x minus x naught is less than r. So we're looking for that distance there. So let's think about this graphically. And we're starting with that x equals 0. So let's graph these points. So we're looking at 0, here's here. If we graph 1 plus 2i, this is our imaginary axis, or 1 minus 2i, the distance would be the same. So let's just find that distance. So we could think about this as a triangle, and we could find that distance using Pythagorean theorem. So we know from here to here is 1 unit, so that side's 1, this side's 2, so to find that distance, it's going to be the square root of 2 squared plus 1 squared, which is the square root of 5. That distance would be the same for this guy down here. So what this is saying is that each of these series must converge. We're talking about the solutions here for the series solutions. So each of these series solutions must converge for at least where x minus 0, because we're looking at about being centered at 0. This is our part A, would be less than square root of 5. So that's your minimum radius of convergence. There could certainly be something outside of that. We're just looking for that minimum. Now, let's look at what happens about the ordinary point -1. That's going to change our picture a little bit. And I definitely recommend drawing a picture for these so you can see what it's going to look like. So we're still looking at 1 plus 2i and 1 minus 2i. And we're going to -1 here. So we want to find that minimum distance. So let's find that distance. I see a triangle that I can build here. So this side's 2, this side's 2. And those triangles are going to be the same if I look at this distance also, which means that this distance is definitely going to be equal to that distance. So to find that distance, and that distance is the radius of convergence, it would be the square root of 2 squared plus 2 squared, which is the square root of 8, or 2 square root of 2. So in this case, those solutions, that's written in terms of the power series, converges. At least. This is the minimum, that's why I say at least. Our x minus a would look like this. So then we would have that. So there's our minimum radius of convergence. This one's a little bit more interesting, I think, than this one down here. Just because our convergence here was in that real plane versus in that complex plane. So from this point on, we're really going to focus only about ordinary points around 0. We could change things if we wanted to look at things other than 0, but we're really going to focus on that x equals 0 ordinary points. And we're going to find power series solutions for differential equations that's centered around 0.